In this video, we're going to discuss the idea of representing a function as a power series. A power series is essentially an infinite polynomial. Each term of our power series is a coefficient multiplied by a power of our variable x, and our power series is formed by adding together all of the terms. If the power series ended after a finite number of terms, we would have an actual polynomial. And so the only difference between a polynomial and a power series is that a power series continues on indefinitely. The ability to represent a function as a polynomial, even an infinite polynomial, is quite useful in many instances. For example, if we want to evaluate a polynomial for some value of the variable, we can simply substitute that value in and compute the function value with only addition, subtraction, multiplication, and division. We don't need to be able to compute square roots or take natural logarithms or anything like that. We can also easily differentiate or integrate polynomials using just the power rule for differentiation or integration. Since representing a function as a power series can be useful, we're then led to ask the natural question, when can we represent a function by a power series? As with many questions like this, the answer depends greatly on the function that we're considering. Some functions will easily be able to be written as power series, and others will require some more development of mathematics before we're able to do so. To begin to answer this question, we start with a power series that we've seen before and analyzed in a different context, namely the series from n equals 0 to infinity of x to the n, which begins 1 plus x squared plus x cubed, and so on. You hopefully recognize this power series as having the form of a geometric series. In particular, if we were to substitute some constant r in for x, then the resulting series would be a geometric series with ratio r. Since this power series has the form of a geometric series, whenever it converges, we know exactly what the sum of this series will be. It will be the function 1 over 1 minus x. This is the sum of a geometric series where the initial term is 1 and the ratio is x. However, this equality is not always true. 1 over 1 minus x exists for any number other than 1. We cannot substitute 1 in for x on the right-hand side here because we would be dividing by 0, but we can substitute any other number in for x. However, in the power series, we know that we'll only get a convergent power series when our ratio, which is the number being substituted in, will be less than 1 in absolute value. And so this particular equality only holds when the absolute value of x is less than 1. Or said a different way, when x is between -1 and 1. And so here we have a function, this 1 over 1 minus x, which we're representing with the power series, the series from n equals 0 to infinity of x to the n, as long as the absolute value of x is less than 1. And so this particular function can be represented by a power series as long as the value of x in absolute value is less than 1. We refer to this power series here as the power series representation of the function 1 over 1 minus x. Now that we know one function and its power series representation, we can manipulate the function and power series here to find the power series representations of several related functions to the function 1 over 1 minus x. In this example, we want to represent the function f of x equals 1 over 1 minus 3x as a power series and find the interval of convergence for this power series. In order to do this, we're going to use the geometric series function that we just discussed. If we generalize this function, notice that we could rewrite the function 1 over 1 minus something, which we'll represent here with just a box, as the power series from n equal to 0 to infinity of that something to the nth power. And in this expression, in this equation, we can substitute any value for that box. And so in this particular example, we have a function 1 over 1 minus 3x. And so here this function has the form 1 over 1 minus something, where that something is the expression 3x. This means that we can write this as a power series of the form n equals 0 to infinity of the something 3x to the nth power. If we wanted, we could then certainly expand this out and write this as the series from n equals 0 to infinity of 3 to the n, x to the n. And therefore, the coefficient of x to the n in this power series will be the constant 3 to the n. And this series is a power series representation for the function 1 over 1 minus 3x, which we found simply by manipulating the formula for the geometric series. If we wanted to write out the first several terms of this series, we can just start by evaluating our formula 3 to the n times x to the n at n equals 0. When we do that, we of course get 1. When n is 1, we get 3 times x. When n is 2, we get 3 squared, which is 9, times x squared. When n is 3, we get n cubed, which is 27, x cubed, plus 81, x to the 4th, and so on. We could continue on with as many terms as we want, but here are the first 5 terms of this particular power series representation. We also want to find the interval of convergence. We're using the geometric series function here, and so we know that the geometric series converges when our ratio is in absolute value less than 1. And here our ratio is the value of 3x. And so this particular power series is going to converge whenever we have absolute value of 3x less than 1. Well, the absolute value of 3x is just 3 times the absolute value of x. And of course, we can divide by 3, being a positive number. And so we want the absolute value of x less than 1/3. And so our interval of convergence here will be the solution of that inequality, which will be the interval from negative 1/3 to 1/3. Neither endpoint is included in this interval of convergence because the geometric series does not converge when our ratio is equal to 1, just when the absolute value of our ratio is strictly less than 1. And that occurs in this case between negative 1/3 and positive 1/3. In this example, we want to represent the function f of x equals 1 over 1 plus x cubed as a power series, and then find the interval of convergence for that power series. Just like in the last example, we're going to use the geometric series as our starting point, which means we want to rewrite the function 1 over 1 plus x cubed to be in the form 1 over 1 minus something. In this case, in order to meet this form and to have the function that we want, the something needs to be negative x cubed. And so if we write this function as 1 over 1 minus negative x cubed, this will allow us to rewrite it, the power series representation for this, in the form n equals 0 to infinity of that something to the nth power. In this case, that's negative x cubed to the nth power. We can simplify this term a little bit by breaking the constant and variable apart. So we'll have the series from n equal to 0 to infinity of negative 1 to the nth power, so that's an alternating sign, and our variable will be x cubed to the nth power, which will be x to the 3n power. So our power series representation here would be n equals 0 to infinity of negative 1 to the n, x to the 3n. If we'd like to write out several terms of this series, we can go about it just by starting with n equals 0 and n equal 1 and 2, substituting them all into our series. And when we do that, we see that our first term is going to be positive, x to the 0, which is 1. We're then going to subtract x cubed, and then add x to the 6th, and then subtract x to the 9th, and so on. And we could follow through with as many terms as we want. To find the interval of convergence, we note that this is a geometric series with a ratio of negative x cubed, and so by properties of geometric series, this will converge when the absolute value of negative x cubed is less than 1. This simplifies to simply being the absolute value of x cubed being less than 1. And this will happen only when the absolute value of x is less than 1, which of course means we're between negative 1 and 1. And so this interval of convergence is exactly the same as it would be for a standard geometric series. We have an interval of convergence from -1 to 1, not including either of the endpoints. If you'd like to try a similar example, you can pause the video and represent the function f of x equals 1 over 1 plus 2x as a power series and find the interval of convergence. Resume the video to see a full solution. We first need to write our function 1 over 1 plus 2x in the standard geometric series form, 1 over 1 minus something, and here that something is -2x. So our function can be written as 1 over 1 minus the quantity -2x, which means our power series representation will be the series from n equals 0 to infinity of -2x quantity to the nth power. We can break off the constant here and write that series as the series with term -2 to the n times x to the n. If we write out several terms of this series, we see that the terms are 1 minus 2x plus 4x squared minus 8x cubed plus 16x to the fourth minus 32x to the fifth, etc. To determine the interval of convergence, we note that our series is a geometric series with ratio -2x, and therefore we know that the series will converge when the absolute value of -2x is less than 1. The absolute value of -2x can be rewritten as 2 times the absolute value of x, and we can divide the inequality by 2 to see that we get the absolute value of x less than 1/2. This means our interval of convergence is the interval from -1/2 to 1/2, not including either of the endpoints.